So in chapter 3, we start to introduce matter and ways that we can kind of deal with it from a theoretical standpoint and be able to put things into a perspective that we can do calculations that are fairly representative of the things that we see in chemistry. So the first thing we're going to talk about is elements, as well as what a molecular element is and what a molecule is. So, atomic elements are those that exist as singular atoms. So things like sodium, right? It exists by itself. There are some elements, though, that do not exist as singular elements. Or if they do, they are so incredibly reactive that they just form what's called the diatomic form, or we'll see there's polyatomic ones. So a molecule is when two atoms are held together through strong bonds, through a sharing of electrons. There are molecular elements, like I said, that when we talk about chlorine by itself, we're not saying Cl, it's actually Cl2. It's two chlorine atoms bonded together through a covalent bond. And there are 7 diatomics on the periodic table that we're concerned with. You need to know these, memorize them. The way that I learned it whenever I was going through this stuff is you have hydrogen, which is obvious, and then if you look at the other ones, they form a 7 starting at nitrogen. These guys here form polyatomic molecules. Phosphorus exists in what's called a tetrahedral conformation. Tetrahedral. As P4. Sulfur exists in what's called a crown conformation as S8. Now, that this isn't to say that sulfur doesn't exist by itself in a molecule. For example, thiocyanate. Right? Sulfur is covalently bonded to carbon. That's totally okay. It's not like it has to be S8. So, atoms can exist in a molecule by themselves, but whenever they are out and about as by them, like completely away from anything else, they exist as diatomics or polyatomics. So hydrogen can be, a part of what would this be? Hydrocyanic acid. Okay, but if you have H floating around by itself with its single electron, it doesn't exist like that. It rapidly will react with another one of these guys and produce H2. So essentially, we can kind of think of molar mass as we get into it as being a composite of all the individual masses. So for example, I always use the example of a car. Okay, a car has a mass associated with it. The mass of the car is one thing. If I and my family have a mass together and we get in the car, that whole thing now is a composite of all of our masses and the mass of the car. So that's where this molar mass and atomic mass thing comes into play. The atomic mass of hydrogen is 1.00794 AMU. The molecular mass of hydrogen is 2.01588 AMU. This would be AMU per molecule. Molar mass is a direct scale up of that, but instead of saying AMU per molecule, we go to grams per mole. So for example, H2's molar mass is 2.01588 grams per mole. It's a direct scale up. So instead of doing singular bits, we're going to do an entire mole. A little bit more terminology. This is kind of interesting. It's a term that you should kind of get used to as time goes by, because things exist differently depending on how they are connected to each other. All 3 of these are carbon. This is carbon, this is carbon, this is carbon. This is graphite, or graphene, excuse me. It's the stuff that's in pencils for lead. This one over here on the right is diamond. The price difference between these two is incredibly different, and their properties are very different. We call these two allotropes of one another. They differ in how they're connected and how they're structured, but they're in the same physical state. Both of these are solids. Okay, if I go from a solid to a liquid, that's not an allotrope. That is a phase change. This one in the middle is actually kind of interesting, but almost completely useless. It's called or it's not a, but it's called Buckminster fullerene. It's also known as buckyballs. It's interesting because carbon has 3 bonds. And that's weird. You're going to find out when you get to organic, that's just strange. So Buckminster fullerene is an allotrope of carbon. All 3 of these are solids, and they're all very different from one another. That's what the definition of an allotrope is. A compound is a little different than a molecule. A molecule is held together by covalent bonds. A compound, it can be a molecule, but it also includes ionic substances. So an ionic substance is held together through the interaction of the plus and minus in between cations and anions, and exists in this repeating lattice. Basically, what we do in order to make it usable is we break it down into its smallest repeatable form. Now, over here on the right, we have molecules. What both of these are 2 or more elements combined in fixed ratios. So water will always be H2O, and it's a bunch of them. Sodium chloride is a bunch of sodium ions and a bunch of chloride ions in this big repeating structure. So here I kind of sum up what the difference between them are. A little bit further on terminology, formulas are just a representation of the number of atoms in each compound. I already mentioned that molecular formulas are relevant to molecules. But what makes a molecule is that it's a self-contained unit. In other words, you don't have water covalently bonded to the next water over. Okay, it doesn't work like that. Whereas with sodium ion and chloride ion, they're kind of all interlaced with one another. And they're all kind of attracted to one another. And what we do is we break it down to what's called the formula unit, which is the smallest repeating unit in a substance. We use this for ionic compounds and some crystalline structures. For example, we could do it with diamond, or you could do it with some of these other repeating crystal structures. The formula mass of a compound is essentially the number of a specific atom times its atomic mass in AMU, and you sum them all up. So for example, carbon dioxide is CO2. It has a carbon atom and it has 2 oxygen atoms. So each one of these has a different mass in AMU. This is 12.011 AMU. Oxygen is 15.9994 AMU. I sum these up and I end up getting 44.010 AMU, and we could put this as per molecule. Molar mass is just this scaled up, but instead of AMUs, we use grams. So for carbon, its molar mass is 12.011 grams per mole. We already said that, right, on the previous page. We did it for hydrogen. So the molar mass for CO2 is just 44.010 grams per mole. For carbon monoxide, I have carbon 12.011 grams per mole. Oxygen for monoxide, right? Monoxide, one oxygen is CO. So I have 15.9994 grams per mole. Sum these up, and I end up getting 28.010 grams per mole. This is how we can do things at our scale. AMU per atom and molecule is wonderful, right? That we can actually think of it in that way, but it's not useful to us. That's so small. It's ridiculous. So instead, we use the grams per mole when we're doing calculations and measurements. So let's try a little bit of calculation here. So how many hydrogen atoms are there in a teaspoon of tert butyl alcohol? So the formula tells us the total number of a given amount of atoms in a molecule. So here, in one of these tert-butyl alcohol molecules, I have CH3 times 3. I have that exterior carbon, and then I have an OH here. I guess it's not exterior, it's the connection point with these methyl groups. So I have 9 hydrogens from that group and 1 hydrogen from here. So the formula tells us how many of each species we have. So I want to know how many hydrogen atoms there are in a teaspoon of tert-butyl alcohol. So I have my teaspoon. Let's grab some other information that I'm going to need. Oh, I already gave it to you because I'm so nice. I already gave you the volume. So 4.93 milliliters of T-butyl alcohol. All right, so we're going to convert to grams. Grams is an easy way for us to get into moles. Okay, that's a very common way for us to get into moles. So for every 1 milliliter, 0.775 grams of T-butyl alcohol. Now I need the molar mass. So how do I figure that out? Well, I need to sum up all of the contributions from here. So I have 4 carbon, so that's 4 times 12, 0.001, or excuse me, 0.011, plus I have 10 hydrogens, so that's 10, or plus 10 times 1.00794, and then I have 1 oxygen, so plus 15.9994, and that gives me a molar mass for T-butyl alcohol of 74.1228. That's my last sig fig, grams per mole. You have to get good at calculating molar masses rapidly. It's incredibly important. You have to get used to just not writing things out like I did on the previous page, but doing what I did here, which is summing them rapidly in my calculator. Okay. All right, so to go from grams to moles, I use molar mass. This is a very common thing. Get used to using molar mass to get the moles. So in 1 mole, T-butyl. Now, at this point in time, I could go from moles to atoms of T-butyl, or well, molecules of T-butyl, but instead I'm going to use the ratio of, for every 1 mole of CH3 OH, I have 10 moles of hydrogen. This is true. Also true is for every 1 molecule of CH3 OH, I have 10 atoms of H. Okay? Both of these are true. So I'm going to go for every 1 mole of T-butyl. I have 10 moles hydrogen, and I want to know how many atoms of hydrogen I have. Notice that we're not using H2 because this is not the hydrogen molecule. This is hydrogen as part of a molecule. So for every 1 mole, I have 6.022 times 10 to the 23 atoms. Multiply across the top, divide by the bottom, and I end up getting 3.10 times 10 to the 23 atoms of hydrogen.